Okay, welcome to the AI in Manufacturing podcast here on Industry 4.0 TV. I'm your host, Kudzai Manditereza, and today we're going to be discussing the topic of causal AI for industrial intelligence applications. And joining me to help us unpack this topic is Daniele Gamba, who's the CEO of a company called AI Send. Daniel, welcome to this show. Such a great pleasure to have you on.
Hi, Kazai. Hi. Thank you very much for having me.
Absolutely. So before we kick things off, could you maybe introduce yourself to the audience and tell us a bit about AI Sent?
Absolutely. Okay. So I'm Daniele. I am one of the founders of iSend as an Italian SME. So we are a team of 28 people now. And we started 7 years ago with just two active colleagues, me and one colleague of study of mine. So it has been a long journey. I'm a mechatronical engineer, and I'm also adjunct professor of deep learning at the University of Bergamo. So I have several roles in my everyday life. So our company develops AI solutions for industries, for mostly for manufacturing industries. So what we do is mostly we are challenged by our customers with the very hard and difficult problems, and we tend to develop new mathematics, new mechanics, new solutions to industrial problems. And when I speak about solution, is because we don't provide only the algorithm itself, so the mathematics, but also we tend to offer the solution to the problem, meaning that we also provide the hardware, we also provide the software, the user interface, etc., etc. So most of our customers are medium to large companies in Italy, manufacturing companies that challenge us with very difficult problem every day, but it's the way we grow and we develop new technology, like probably Causality that we will discuss today.
Oh, yeah, absolutely. Yeah, so perhaps let's jump right into it.
Yeah.
So maybe to kind of begin just to paint a picture for our audience here,
Yeah.
could you explain what is causality or causal inference? I don't know which one is the
Yeah.
right way to really call it. And maybe to kind of explain the differences between your causal inference and the traditional analytics.
Yeah, absolutely. So in these years of AI Center, we developed quite a few solutions from predictive maintenance to quality inspection to process control and optimization. So we've built several projects. And in this time, obviously, you can adopt and leverage the power of deep learning. That is also my matter of expertise. But in some use cases, you face some limitation about the trustworthiness of the algorithm, the reliability, the explainability of the algorithm itself. So there are some use cases when deep learning as a very powerful tool, as we see it today and every day, and so like for example, with LLMs now and VLMs and the agentic approach. This is obviously the new big trend. But there are some questions in the industry that could not be answered without a deep understanding of what the problem you're facing. Okay. And so it is very important to always know and develop the technology that better fits that use case in particular. So for causality, obviously, the causality, causal inference, probabilistic graphical models, there are Bayesian networks, there are a lot of names around causality. But it's a very powerful tool that you use to answer some specific question. And maybe that question is, what is the root cause of a problem? Or how much a factor, an intervention actually have an impact on the process. So it's very important to use causality when the question is, what is the root cause? So how we can go back to the process, to the machine, and identify the root cause of the problem. Or when we want to simulate, for example, what would happen if something occurs? Okay, so this is a class of algorithms that is quite distant from the LLMs, from the deep learning algorithms that are way smaller and way more refined to answer just that question. Okay. We started this exploration about causality almost 3.5 years ago, 3 to 4 years ago, because we were doing a very large predictive maintenance project for a OEM, for a machine builder. Okay, that this large OEM let us use a laboratory machine, so we can tamper with the machine, try to introduce defects, introduce problems, and we observe to the data how actually things worked and what we would have seen if there was a problem on a cushion, on some drives, actuators, etc. So we developed algorithms for like 9 months with data, etc., with very specific diagnostic cycles. And then after 9 months, we had our own algorithms and we were testing the algorithms on the machine. And one day we go back to the customer, and that day in particular, every algorithm was telling us that the machine wasn't okay. So the machine was running badly. All the algorithms were telling, yes, there is a problem. Okay. Also, the customer, the OEM technicians told us, yes, there is a problem with this machine, but we don't really understand what is going wrong. Okay. And at that point, obviously, neither us nor the customer technicians were actually understanding and figuring what was going wrong with the process. So they called that the expert. They called the senior one, the Matteo that came to the machine, touched the machine, imposed with the hand on the machine, moved the machine, and immediately recognized that the machine is not perfectly on the plane, on the ground, and then leaves. Okay, like in 10 seconds, he diagnosed a problem that we and the customer technicians weren't able to diagnose in 1 hour of work. Okay, in 5 seconds. Okay, for us at that point, we spent like 9 months developing the most beautiful AI algorithms for predictive maintenance with synthetic data, with very complex algorithms, etc. But at that point, we have been beaten in 5 seconds by an expert. So that was the moment when we decided, okay, we want an algorithm that reasoned the same way that he did, because he was way more performing without any data, without seeing in the 1 kilohertz sampling time from the drive, from the actuators, without anything. He touched the machine and he understood. Okay, so 3 years ago, 4 years ago, we started with this idea to find algorithms that reason the same way that the technician, that the Matteo, that the expert one do. Okay, so we go back to study and we learn about causality. That was a trend since 2017, a very small trend 4 years ago. And then we started to learn, started to think, okay, maybe this is the way to actually implement inside the algorithms the same reasoning. So what we want to mutuate, to learn, is not the data, is not the actual intervention. We want to learn the way that the expert reason in front of a problem. Okay, so this is the idea and our journey. Obviously, there are several approaches to causality. Our aim is to have like a digital companion that learns and thinks the same way of the expert. Maybe with less skill, maybe with less data, maybe with less performance. without aiming, neither aiming to reach the same level of comprehension. But if we have an algorithm that reason and tells the operators and other colleagues, okay, in front of this problem, you have to do this because of this, and I mutuate from the expert the same reasoning process, I can actually achieve a higher, better result. And this has been the last 3 years for us. So we developed this causality solution to find root causes. And it's a very simple one. It's just a graph, but it mutuates and learns directly from the reasoning process of the expert and not from the data. The data comes later, and it's very helpful, but it's something that you couldn't have and still have something that is working very well to diagnose process problems. So the idea behind causality is that if you, this is causality in general, if you don't know specifically how your world works, how your problem works, for algorithms that observe column A and column B in a data set, they have no understanding of causal relationship. They could at best measure correlation and do not understand if it's the presence of police causing the crime, or if the more crime in an area that causes more presence of police. There is no possibility for an algorithm that just observes the data to understand causality. So the path are two. There are two options in these cases. Or you let the algorithm experiment. That means in some cases you create a little criminal and go around and try to see if it causes more police presence. It's not very feasible, but and also in industry it's not very feasible. Or the other way is that you share your knowledge about causality that you already have with the algorithm. So you don't just give the data, you also give the structure. You give, okay, this factor impacts on this other one. And this is the cause, for example. If you go beyond just giving a data set, a data frame, and give also the domain expertise, your algorithms will do like crazy amount better performance.
Oh, that's really fascinating. And I guess my question is then, the goal really for you here was to, as you put it, reason like the way that Matteo, sort of like
Yeah,
reasoned about a problem,
correct.
and and Matteo got to that realization because of, say, 20 years of, working through the same problem, and also knowing what else is happening on the other side, of the factory, or what else could be causing that problem. So obviously they've,
Yeah.
got that idea of causality. So for you to be able to train your algorithm to reason like that, does it mean that is it sort of like shadowing the technician and capturing data as they do, or how does it work? Maybe on a kind of like technical level.
Absolutely. No, it's just very simple. It's just asking the expert how you reason in front of a problem. So it's just asking the technician to design a graph of causal relationship where there are factors that impacts on other effects, and there are causes that impacts on effects. And there is a big graph growing. It's just that is asking the expert to do something more, not just giving us the data, but also the reasoning that there is behind the data. It's previous knowledge. Also, Matteo has not only 20 years in experience in the industry, has also like a few thousand years of evolution. That is something that for us, understanding causality is very simple. It's like in every day for us. But for machines that has evolved in the last 4 years, trust me, is still very difficult to understand causality. So this mechanism that is also, I think, uh, Newton or a big philosopher was telling us that human reason by cause and effect. So it's something that is in us, inside of us. But it's very hard to understand why a machine cannot do the same. Okay, and
Yes.
with LLMs, it's even harder to understand if the system you're referring to and you are interacting with has the same level of understanding that you do. And most of the times the answer is no, because with regression models, uh, if I have third factors that are called confounders, could disturb my interpretation of the data and could cause um, uh, bad anomalies that do not share the same principle that we do. But if we ask the expert, maybe we are sure to consider all the factors because he already knows. And just the problem is to translate the knowledge that he already have into graph. Okay, and this is most of the problem. So it's the hardest problem, obviously,
Yeah.
because there are skill issues, because there are different interpretation, because there are different technicians that learns different way in the way they live, and also because there is a little bit of culture about the change and culture about the digitalization, because we are not aiming to digitalize the processes or collect KPIs. We are aiming to digitalize the reasoning in front of a problem. And so it's sometimes is a challenge culturally because you not very much from the technician itself, but for the company, because you as a company, you have to understand that the expertise that there is in the expert's mind is an asset, is something that intangible. But I have several customers that can assure me that if the key person, the key technician leaves the company, they lose 20 to 30% of performance. Okay.
Yeah.
So, and these are maybe steel manufacturer. So very large industries that lose on production processes 20 to 30% if there isn't that person. Okay. So it's crazy, but it's something that culturally has not been very well received. The expertise of your people is an asset that values the 20% of your turnover and is way more valuable than that the asset itself, that the machine, that the plant itself. Okay. And sometimes companies, not technicians know it very well, but companies do not understand very well this part.
Okay, absolutely. So maybe to kind of like help, companies or leaders of companies to better grasp the idea of, causal inference or the superiority of causal inference, could you perhaps share an example of a real-world manufacturing challenge
Yeah,
that would be
absolutely.
difficult to achieve with traditional deep learning and more solvable with causal AI?
Maybe I can share the screen, obviously, for your
Yes, please.
listener. It will be harder, but very briefly, I will share my screen. So also to visualize what is causality and what is a causal graph. Okay, so in this case, this is in Italian. I will translate it for you, but there is a process problem for extrusion blow molding. So we are doing bottles in this case, and we could have a problem, a trouble that is black spots. Okay, so black spots in extrusion blow molding is a process problem most of the times, and could be related to materials, to residuals of material inside the machine, or could be something related to the machine performance. And maybe machine performance is something that is related to temperatures, to filters, to lack of material volume, etc., etc., and or if the machine was just turning on, etc. And we designed this causal graph with few experts, with 3 experts from our customer, And this is the causal graph that just tries to understand which is the root cause of a problem. And in this case, it estimates as more probable that is something related to materials, and it's less probable that is something related to performance. And if we are looking into the part of the graph that is related to materials, it's also estimated that it's 70% more likely that you are doing recycle HDPE, okay? Because obviously recycled products has more impurities, okay? So in this scenario, we have designed the causal graph using the experts' knowledge. Then we ask them, give us a prior of probability. That means how many times, if you see black spots on the bottle, most of the time it's just material. 8 out of 10 is something related to materials, and 2 times out of 10 is something related to the setup of the machine. And maybe only 1 over 100 or 1 over 1,000 problems is something related to thermocouples on the extrusion, on the extruder. When you map this reasoning, then you can create a little chatbot that you see as a demo in the left, in the bottom left of the screen. And the chatbot start asking me what kind of polymer are you using? And we are using HDPE, so it's something that okay, maybe it's not, maybe it's clearer, so it's not a problem about materials. And is the operator senior or junior? No, the operator is a senior one, okay? Maybe it's the quality of the material. No, it's not the case. How is the extruder material going? Yes, it's going okay, but was inactive and yet in temperature? No, maybe I don't know it, okay? Is the milk contaminated? So in this way, you're building a process of just a causal graph that just ask the question to the operators, okay? To support the troubleshooting, to support the setup of the machine and the starting phase of the production. You are not building something that is crazy hard. It's just asking the right question to the operator. And this is the reasoning part.
Yeah.
Every time we found a case, obviously, we store a session and we store some data, because at some point also the deep learning teacher also needs some data. And in this case, we stored a few examples where actually there was a problem, and we found the root cause and found the solution. So the idea, the first 8 out of 10 is materials, and 2 out of 10 is temperature setting, maybe shifts during time, and we learn from the data that is 7 out of 10, 70% related to materials, or 65, and is something maybe is more lacking on the maintenance part, okay? So we learn, we support the operators during the test phase, and we also obviously collect data to update this kind of probabilities in time, going on and on. So this is just a very simple use case of causality. It's just the first, let's say.
Yeah.
We will develop on this technology, but just to show you and to touch with hands and see it actually in performance, the graph is designed with the expert, and then data is collected during time while using the platform, using the chatbot, for example. Also easy, feasible, and also very usable from smartphone or tablets or HMIs on the machine. It's not obviously the overall graph for the operator.
All right, perfect. So yeah, I mean, we're going to discuss the METI platform
Yeah.
in a bit. For now, I just want to kind of like get some clarifications
Yeah.
on a few points. So the first question is to say, so basically on that platform. Yeah, yeah. Are you then going to first of all build a model out of this information? Do you at a point say, okay, now we've collected enough, let's build a model and start to perform inference? And number two, the main reason why I asked that is to say, for example, there is Matteo might be 20 years experience, but there's some problem that he's never met because manufacturing is so complex. How does causal AI account for the unknowns in this case?
Yes. Uh, so for the first part, obviously, the model, the graph that you've seen is already a model, is a probabilistic graphical model, is based on conditional probabilities. Uh, and the once we collect the data, we actually update all the probabilities that you've seen in the graph. So this is already a model. Obviously, you could have more complex ones behind the backend with a neural network built the same way or something more complex. But the one that you've seen is already a running model, and the probabilities are actually very close to reality. So it is pretty true that 60% of black spot problems are related to materials for that customer of ours. So we already learned probabilities from the interactions. And for the second part, yes, there are two kind of learnings. So Matteo has seen a few use cases during his years and has explained his knowledge so far in the platform. But going on, there are two more way to learn. One is just the probability adjustment. So I collect more and more use cases, more and more examples of the actual causes and troubles that I have in production. So I update more and more the probabilities. And this is very easy as it's done by the platform behind the scene. The other one is, okay, but maybe at this point we discover a new root cause, okay, that is not mapped. At that point, the new operator or Matteo itself just clicks on add a new graph, a new model, sorry, a new node on the graph, and himself draws the arrows that define how probability flows in the graph. Okay, so whenever you find some new effect, some new causes, some new mechanism, you just add the nodes that you are missing and draw graphically the arrows. And later on, when you instead collect actual data about that problem, you will update the probabilities. So it's a two-way. Obviously, since before I was mentioning the culture of the company this is a very challenging stuff to do in the long run. You have to structure yourself to see knowledge as an asset, meaning that you will have people, knowledge managers that actually implements and keep running this cycle of providing knowledge, collecting data, collecting feedbacks, updating knowledge, and going on and on. This is a virtuous cycle if it's done correctly, or can end very, very badly if you don't provide enough value to the operators. They will not use the platform. If they do not use the platform, they won't collect data, so they won't have value back. Okay, so it's very it's an important problem of change management, of engaging operators, because if the operators and the technicians and the experts and maintenance uses the platform, they will go through a virtuous cycle that it will improve more and more the knowledge that the platform has on your processes. But if you stop running, stop spinning the wheel, everything stops, the operator won't use the platform, technicians won't update the knowledge, etc., etc. So everything falls apart.
Absolutely. Okay, so you've given us a sneak peek of the METI, which is your causal inference platform. But for now, I'd like us to take, a deep dive and, give us an explanation of, the core component of the platform. What is
Yeah.
it composed of? How does it work? How do you deploy it? And so on and so forth.
Yeah, absolutely. So I will go back sharing my screen. So METI is starts from a workspace where you map all the graph that you want. There are several in this case. Also, there are some that is in this just for explaining the probabilities flow from medical examples. Causality has been in the medical domain to assess treatment estimation. And then you have obviously the main component is the graphical part. Then we can have the sessions, so also the data that we collect from our patients or from the processes. And also we could have all the part about the troubleshooting, and we can create new versions. It's very boring for me to say, also for listeners, because there are quite a few tools inside the platform to, let's say that mapping skin cancer is a problem, and we can map it and start a chatbot that asks questions to diagnose skin cancer in this case. And then you have versioning, you have quite a lot of features inside the platform. But the platform itself is just having a few examples, a few nodes connected through arrows that are directional, and you can create easily a directional acyclic graph that describe your problem. In this case, there is this is an example, academic example to show probability flow. So whenever you have skin cancer, let's say skin cancer and ibuprofen, the medicine, is very related, is very correlated, okay? And if I observe a high use of that medicine, I will observe a higher rate of skin cancer. And if I observe a low use of that medicine, I will observe a drop of 0.9% of incidence in skin cancer. This is correlation. So these are the data that you find inside the table. Obviously, there is not a causal relationship between these two. There is a third factor that is, in this case, age, that allows the probability flow. So whenever I know that a person consume quite a lot of medicines, I also can estimate that that person is older. And if it's older, there is a higher probability in skin cancer. And if I know for sure that it doesn't assume medicine, so it's very low, its consumption, I can estimate 50-50 is younger or older. And in this case, since I observed that I estimate a lower age, I can also estimate a lower risk of skin cancer. Okay, but if I know for sure that my patient is young, there is no change whatsoever of the risk of skin cancer, if I know that that person consumes a lot or no medicine. So this flow of probability is the actual trouble in processes in industrial setting, because factors like this one, like age, that are called confounders, are very frequent. There are tons of confounders, hundreds of confounders inside a facility, inside a production plant. And maybe they do correlate data observingly, but they do not reason that there are cause and effects inside the production plants. We had a customer, a very large furniture manufacturer, where some operator tended to use different settings when they observe the production lot from a particular supplier. Okay, so and there was absolutely no meaning, but they let's say learned that supplier provided them harder woods. Okay, it doesn't make any sense because there isn't really for that kind of production harder wood to be processed with a machine. But they learned that they had that confounder. So whenever they observe that supplier, for example, or that machine or that material, they tend to use different settings. And this is a very hard observation when you do studies on your production, when you want to optimize your production, because you will have a lot of data that tells you, look, the medicine causes skin cancer. And it is not true, but if you will never know it if you don't design a causal graph and you consider all the factors inside your production process. Obviously, this is also very, because you were asking me, okay, but what if we know that skin cancer has something to do with genetics? For example, we can add a new node, genetics, that is good or very bad, okay? And there's something, or maybe neutral, okay? And we can, let's say, something related to genes. And I can create my node. I can draw the arrow that impacts, because obviously genetics has an impact on skin cancer, but has not an impact on the consumption of ibuprofen. I suppose I'm not an expert in this field, very. And I also have to give a prior probability. So how much of population has good genetics? Maybe 50%, neutral 40%, and there is a 10% probability that you have very bad genes, okay? At this point, we have completed that first part. When I was telling you we need that prior to, say, out of 10, 70% is materials, 20% is the machine or the operator setting, etc., etc. You have to give that prior, and then we can learn from the data and interact with the process. Obviously, this is a very, let's say, simple example. We have more complex one, but the black spot example, like this one, this is a very real world process problem for extrusion blow molding. So bottles that have black spots and neck occlusion. So it's another kind of problem for that kind of process industries.
Oh, yeah, absolutely. So, I mean, clearly, causal AI and your deep learning share a common problem, because they all need data to some extent and in many different formats. And the reality is that in manufacturing, a lot of data is siloed. There's a lot of proprietary interfaces. It's not really easy to integrate data into across different systems in manufacturing. Can you speak to us about the challenges of data integration in manufacturing, and solutions that you have for that?
So we are more focused on the actual answer and not very much on the collection of the data, something that we ask our customer or our partners to do. So we tend to work hand by hand with partners that has way more expertise than us in collecting data. Obviously, uh, we see data as a tool to answer very specific questions. So, should I improve that line? Should I do more maintenance? How do I achieve better recipes or better cycles for my products? And these kind of questions are answered also with data. And you obviously to be effective in that way, you will need infrastructure, you will need software, you will need the IoT, the industrial IoT solution to actually collect data when you have to answer that question. So we tend to work with partners. We do not have our much expertise in the data collection side. But once we partner up with other colleagues, we can be very effective. For the customer, for the industries, you have to be ready because I'm not a fan of collecting all the data without any real reason, but just let's collect data, then we will extract value. It doesn't work very much like that because maybe you collect a lot of data and then you have the wrong sampling time to answer the question. So you have useless data or you don't have that variable collected or something else. And it's very frequent in industries. So to me, it's way more important to choose the good technologies, the stack that layer up and give you the foundation. So whenever you have to answer a question, you will already have all the parts that you need to collect data to answer that question. So it's very important, but something that I'm not the one to actually suggest you how to do that. It's important to have in place your infrastructure and to be ready, but it adds a lot of value whenever you have a business case to answer. If you don't have a business question, it doesn't bring any value whatsoever.
Yeah. So maybe talking about the business cases. Do you have an example of a real world use case where your platform has had the most
Yeah.
impactful?
Yeah, absolutely.
Impactful?
For example, I was talking before about that large furniture producer, kitted furniture. I don't know it's the correct term. Um, on the experimentation phase of the project, whenever an operator found a problem on the production lines that was mapped inside METI, with the data collected from the machine and the knowledge from the other colleagues, we divided by 3 the time of stop. So we had like minus 66% stop time. So for that kind of production, when you have thousands of stop time per month on production lines, obviously a lot of production lines, obviously a very big customer. Reducing that period means at the end of the year, a few million euros of saving, just asking the correct answers. It isn't any harder than that. It's just a tool that asks you questions, the correct questions. And if you give the 2-3 answers and collect from the data the real objective data that you already have, the sensors, the PLC, the recipes, etc., you can do a third of the time. So it's 2/3 less stopping time. And this also means less discard for quality because you are more effective in the setup of the machine. So this customer is a very good one of ours, a very large manufacturer, very well known. We are also working, for example, for with another very big steel manufacturer here in Italy, but it's a global company. And another very big OEM in injection molding. Okay, so all companies way above the billion euro turnover, and for injection is the same. You have process problems like black spots or bubbles or other problems, and you have to be effective in solving that kind of problems. Obviously, these companies have tried before us different approaches. Have tried LLMs, have tried machine learning models, etc. And then they adopted this causality way, because whenever you are in production, you want something that is very reliable, that is almost deterministic, that is easy to be explained to the operator, because otherwise, if he doesn't understand, it's a problem also for the operator. It's not a machine that is there. He needs to understand, he needs to be involved in the project. And also that they tend to do not accept the risk of giving the wrong suggestion. So LLMs and RAG are very powerful tool. And we also use them, and also inside of METI to look inside manuals and to give support to the creation of the graph. But whenever you are in production, if you suggest an operator to do the wrong thing and you're a steel manufacturer, the risk of causing millions of euros of problems, of damages, is very high. So they want in production something that is less powerful than ChatGPT, for example, way less powerful, but very, very reliable and 100% sure that they won't ever give the wrong suggestion to the operator. Maybe it stops before, but it won't give you the wrong suggestion.
Awesome stuff. Okay, so like for any manufacturing leaders who may be, listening to our conversation right now, and they're thinking of adopting causal AI for their use cases, could you give us, a picture of what that implementation roadmap looks like from the time they engage you, and what kind of like what that looks like?
Yeah, absolutely. So the project itself, so there is the license of the platform, obviously, and then there is the first phase that we call delivery, that is the training of colleagues, of knowledge managers, the setup of the internal processes of the industry to actually create this flying with this virtuous cycle, and then the first problems addressed together with our team and the customer team. This is a time span of 3 to 6 months. So we partner up with the customer for 3 to 6 months. We design a few use cases, and then we go in production because it's very fast. Production for us is just having or the tenant on our AWS instance, or installing the platform on premise. Since we are dealing most of the times with very large manufacturers, they tend to have their own data center, and they want the platform on premise. It's also very critical expertise, a very critical knowledge. There is inside an asset that is valuable like 20% of efficiency of production line. So when a competitor could access the same data is very critical. And it's very simple to understand because there is the recipe of the expert inside. So we are very happy also to do on-premise installation. And in 3 to 6 months, we are in production, and we have the first few problems diagnostic. Then, obviously, there is the big part that is the customer technicians, the customers' knowledge managers that have to continually introduce knowledge inside the platform and keep it growing, etc.
Awesome stuff. And then can you speak to us about how you sort of like approach the use case typically? Do you maybe say pick one machine and start with it, or pick one line? And kind of like the reason why I asked that is to say, how then do you kind of like scale out to say if you start with a machine, a line, how do you scale out to multiple factories?
Yeah. In most cases, we pick a production line, and we tend to have to cover problems across all the production line because you then see how easily is this kind of reasoning across all different problems, so from the setup to the assembly to the conduction of the process to the recipes, etc., and the troubleshooting itself. So we pick a production line, we diagnose and create the digital twin of the expert for that production line for different phases. And then we release it. So it's easier to see, okay, I have to scale it from one production line to 150. It's easier to see the potential outcome. And the potential outcome in this case, most of the time, a very big saving.
Cool stuff. And then just two more questions before we, wrap it up today quickly. I noticed on your website you also do some work with in the pharma industries. I
Yeah.
want to kind of like get your sense on how do you, normally build trust, or how do you sort of like suggest, manufacturing leaders build trust in AI, and kind of like, advocate for it internally, especially in highly regulated industries like in pharma.
Yes, like before, the big advantage of a platform that is deterministic. So you have probabilities only for computation, but not in the outcomes. So if something there isn't map, it won't be asked to the operator and won't be searched for. Okay, so pharmaceutical companies, we work with the couples and also an OEM in pharmaceuticals. Uh, they are always looking in production to very reliable because to solutions because it's very norm, it's very strict. You cannot do anything wrong. And METI, it's very useful in that sense because it won't ask you anything that is outside of the platform. It's not a generational question. The question there is there because an expert put it inside, an expert wrote it down, and is like the same expert that you call, I have this problem, and start you asking a few questions. So pharmaceutical companies are in that sense way more easy for a platform like METI because it's very deterministic. Why? If you have like automotive, for example, where you have so many different problems, so many different causes, it's harder also to design the causality of the production line. When we are talking about processes, and processes is pharmaceutical, steel, woodworking, plastic, and your process is very confined, then you have your process expert for that part, and he will ask you the top 10, 20, top 20, top 30 question to diagnose the problem. If it's outside of this scope, obviously you will still need the expert. It's not that you can say goodbye to the expert. It's not something that you will ever have to. But if it's inside the top 20, top 30, top 50 problems that you've mapped, then you will find it with a couple of more, couple of less questions. And so it's very easy for pharmaceutical companies. We have one of our first customer was this OEM in pharmaceuticals.
Oh yeah, absolutely. And then lastly, to conclude this conversation, do you perhaps have any words of advice for manufacturers about the adoption of AI? How should they approach it?
Yeah. So for sure, AI is the most beautiful tool. But also to me, obviously, but in general, is the revolution that we are living now. So it is a very big discontinuity in time, and you need to experiment, you need to understand, it's something that everyone needs to understand and experiment and learn about AI, because it's something that is changing dramatically the way companies work. Okay. And if we go a little bit further in time, and if we look at the future, we are working not only on causality, we are working on vision, we are working on planning, we are working on process control to create not autonomous industries, because it's unlikely that we will reach like level 3 autonomous driving, okay? But it's more likely that we will achieve cruise control, no? Like in the highway, you keep your line, you keep your distance. Okay, so industrial facilities for some aspects are even easier than most of the highways, for sure in Italy. Okay, so it's it, it, it could be easier in that sense. And we as iSent, but a lot of companies are working to create the cruise control of production plants, of production processes. So in order to achieve that, and this is a prospect for us, a projection of 5 years, and 5 years is very close in time, I learned. But to achieve that, obviously, you will need to start now understanding, start now experimenting, failing projects, and then better learn about this transformation that is a big discontinuity that has no coming backs. So industries will be different for sure, but you have to start now to understand where we are going.
Absolutely. Such an exciting future of manufacturing with AI. So we
Yeah.
will provide links to your social media and website in the description of this video and audio for any of our audience who may want to reach out to you. So Danielle, it's been such a fascinating conversation with you. Thank you so much for taking the time to join
Thank
me.
you, Kudzai. It was very pleasure to talk with you.